All right, chemistry, let's take a look at your video lecture for chapter 11, section 4. This is going to be yet another very, very short video, right? The idea is very simple. The number of tasks that you're going to have to complete aren't that significant, especially because we've already been dealing with gases for 2 chapters now. This will be the last of our second chapter in gases, right? We know a lot about gases. This isn't our first rodeo. We know how to work with gases. So at the end of this video lecture, I want you to be able to state Graham's law of effusion. I want you to determine the relative rates of effusion of 2 gases of known molar masses. So that means if you know their molar masses, basically I'll give you the formula and you can calculate the molar masses using your periodic table. You're going to use Graham's law to determine the relative rates of effusion. And then lastly, state the relationship between the average molecular velocities of 2 gases and their molar masses, right? How are their velocities and masses related to one another? Is it inverse relationship or is it a direct relationship? So we actually did define diffusion and effusion way back in chapter 10 when we first started talking about gases, but let's remind ourselves what they are. The kinetic molecular theory states that all molecules are in constant motion. For gas molecules, there's even more motion. They're a higher kinetic energy form phase of matter. So the constant motion of gas molecules causes them to spread out to fill any container that they are in, right? They spread out. This gradual mixing of 2 or more gases due to their spontaneous random motion, remember those from the assumptions of the kinetic molecular theory, is known as diffusion. This gradual mixing is known as diffusion. But pay attention, you have to have at least 2 gases present, right? In order for them to mix, you have to have at least 2 things. If there aren't 2 things to mix, right, it's just expansion. It's just expansion. The fact that we're mixing makes it diffusion. Effusion, while it sounds very similar and as a related idea, is pretty darn different from diffusion. Effusion is the process whereby the molecules of a gas confined in a container, right? Like they're in a tire, they're in a jar. They're confined in a container. They randomly pass through a tiny opening in that container. So the way I think about this in my head is a bike tire. Riding my bike out in the country when I was a little kid, you'd roll over those little goat horn stickers or little puncture vines, whatever you used to call them, but they would have these little teeny tiny sharp ends on them, and they would puncture your tires, right? They'd make your tires go flat. Now, it wouldn't explode your tires, but that tiny opening, that tiny piercing that little puncture vine did to your tire, made in your tire, is going to allow gas to escape through that tiny opening. It's going to take some time for all that air to get pushed out, because the gas molecules are moving randomly. They don't move purposefully towards that tiny opening to move through it. They move randomly. So they have to randomly pass through that tiny opening. This is known as effusion. So let's define Graham's law of effusion, right? We know what effusion is. We know what diffusion is. Let's get to Graham's law. Rates of effusion and diffusion, right? How fast do they effuse? How fast do they diffuse, right? These gases. All of that depends, the rate depends on the relative velocities of the gas molecules. If the gas molecules are moving faster, they're going to randomly encounter that tiny opening more often, faster. And so the air is going to get pushed out of the tire faster. It's going to deflate faster. If the individual gas particles that are mixing together are moving faster, they're going to diffuse faster. Because remember, diffusion is the random gradual mixing of 2 or more gases. The velocity of a gas varies, remember, inversely with the square root of its molar mass. Okay? It inversely varies. Inversely. As one gets big, the other one gets smaller. But not straight across, not a straight up inverse relationship. There's a square root involved. We have to take the square root of its molar mass and then invert it. That is going to be your velocity. So recall that the average kinetic energy of the molecules in any gas depends only on the temperature. Remember, kinetic energy is proportional to temperature. When temperature goes up, kinetic energy goes up. When temperature goes down, kinetic energy goes down. And kinetic energy is equal to 1/2 mv squared, where m equals mass and v equals velocity. So, with that in mind, because we already know that, one of the assumptions of the KMT, for two different gases, let's just call them A and B, doesn't matter what they are, at the same temperature, as long as they're at the same temperature, and remember, temperature is proportional to kinetic energy, that means the kinetic energy of both gases will be the same. They're equal. And if kinetic energy is equal, that means the two statements of 1/2 mv squared are also equal to one another. And we can use this equation here. 1/2 m of A times v of A squared is equal to 1/2 m of B times velocity of B squared. And we can solve for mass and velocity. So continuing on with Graham's law, right, and how you're actually going to use it to determine the relative rates of effusion from the equation relating the kinetic energy of two different gases at the same conditions, we can derive, you're not necessarily going to have to derive it in this class, but you can derive an equation that relates the rates of effusion of two gases with their molecular masses. This equation is known as Graham's law of effusion, right? And so we have that 1/2 mv squared, okay? Physics thing, very, very important, crazy important. But Graham's law is an application of 1/2 mv squared, okay? And it states that the rates of effusion of gases, as long as they're at the same temperature and pressure, are inversely proportional to the square roots of their molar masses. And you'll notice in this equation, rate of effusion of gas A is on the numerator, but the square root of the molar mass of A is on the denominator on the other side of the equal sign. Conversely, or maybe inversely I should say, notice that the rate of effusion of B is on the denominator on the left side of the equal sign, but the square root of the molar mass of B is on the numerator, the right side of the equal sign. Right? It's an inverse square root relationship. Inverse square root.
The rate of effusion of gas A over the rate of effusion of gas B is equal to the square root of the molar mass of gas B over the square root of the molar mass of gas A.
And that's it. So, Graham's law. In application, this is going to be a problem that you see very, very commonly with Graham's law. If we have this tube, right? We have cotton plugs moistened with ammonia and hydrogen chloride. Were placed at the opposite ends of this glass tube, and several minutes were allowed to elapse. Okay. Now, the reason that they're cotton plugs is not important. All we're saying is that on one end of this tube, ammonia is flowing, right? So on this picture, ammonia is coming in from the left, and on the right, hydrogen chloride is coming in. Again, so we have one gas coming in from the left, one gas coming in from the right. Okay, so we need to understand this setup. Now, over a few minutes, gases will move, right? Why? Ask yourself again, we're trying to look at Graham's law. Why does the white ring of ammonium chloride form closer to the right end than the left end? So again, what are we seeing? When ammonia reacts with hydrogen chloride, which it does, it creates ammonium chloride. And you can see ammonium chloride. That's the important thing. And so this area we see about 2/3 of the way from the left to the right is actually the location where the two gases are mixing, right, to create this product. The question that's being asked here, why is it forming closer to the right than to the left? Meaning, why doesn't it form right smack dab in the middle? Why is apparently ammonia traveling further in the glass tube and hydrogen chloride traveling a shorter distance? Well, remember what Graham's law is stating, that the relative rates of effusion are inversely proportional to the square root of the molar mass, meaning the heavier a gas is, the slower it will move, and the lighter a gas is, the faster it will move. Well, if you look up at the periodic table and do some quick calculations, molar mass, ammonia is lighter than HCl. So that means it's going to move from its source, the left side, to the right faster. So over the same amount of time, it's going to travel further distance than ammonium chloride, a heavier, more slow-moving species. So let's do a sample problem, because we actually have to do stuff with this law. We have to do calculations here. Compare the rates of effusion of hydrogen and oxygen at the same temperature and pressure. Again, we have to say same temperature and pressure so we can actually compare them. So remember, hydrogen, H2, oxygen, O2. So what we know the identities of the two gases that we're talking about. We don't know the relative rates of effusion. That's what we want to find. So how are we going to do this? The ratio of the rates of effusion of two gases at the same temperature and pressure, again, that condition has to be met, same temperature and pressure, can be found using Graham's law, right? Which is represented as the rate of effusion of A over the rate of effusion of B is equal to the square root of the molar mass of B over the square root of the mass of A. Remember, it's inverse, so they're flipped. A is on the numerator on one side, on the denominator on the other. B is on the denominator on one side, it's on the numerator on the other. Remember, it's an inverse. So let's do this. When we substitute the given values, because we were given those values by knowing the actual species, right? We know that each hydrogen atom has a mass of 1.01. Each oxygen atom has a mass of 16.00. And so we can calculate the molar masses just by knowing the formulas. We substitute those values in for molar masses, right? The molar mass of B and the molar mass of A. So I have 32 grams per mole for O2 and 2.02 grams per mole for H2. If I divide those out, right, the 32 divided by 2.02, okay, you're going to get about 16. It'll be a little bit off because by a certain decimal, but then you have to square root that number. Okay, square root that number. It's going to be when you divide out 32 by 2.02, it's going to be a little bit less, just a little bit less than 16. So when you square root 16, something that's a little bit less than 16, you get something that's just a little bit less than 3.98, a little bit less than 4, I should say, 3.98. So our answer, our response, is that hydrogen effuses 3.98 times faster than oxygen. Notice that I don't have a velocity. I'm not saying it's moving at this speed, because we're being asked for the relative rates of effusion. How do they relate to one another? Well, they relate by a factor of almost 4, 3.98. Hydrogen is faster because it's lighter. Oxygen is slower because it's heavier. How much slower or how much faster is hydrogen? Hydrogen is 3.98 times faster than oxygen. And that's how you phrase the comparison, that relative rate of effusion.